Yeah, okay. So I am clearly audible,
Yes.
and you also see? Yeah. You can clearly see the slide. Can you clearly see the slide?
Yes,
Yes.
sir. Yes, sir.
Okay. 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 So yes. Okay. So let me start today's session, which is related to assignment of week number 4, and this course is entitled as application of spectroscopic method in molecular structure determination. And let me introduce myself. And I am Moina Ghoshal. I am a PMRF at ISER Kolkata, and I have been assigned as a TA for this course, which was instructed by Professor S. Sankararaman, which is based on various spectroscopic techniques that you actually comes through when you were doing any kind of organic reaction or something. Whenever you do, you need always spectroscopy. So in spectroscopy actually has very much application in physics, physical chemistry, and also in organic chemistry. But mainly dealing with the organic molecules or organic structures, you need spectroscopy much more uh, in organic chemistry. And this course actually deals with the spectroscopic things that happens when you are dealing with some organic molecules. So in the previous 3 week assignments, we have shown that how enema spectroscopy is built up, and how it is helping to solve some problems, to get some insight about the structure, about the stereochemistry, how it is behaving at different temperatures. All of these things were very much clearly understood using enema spectroscopy. Okay, but the NMR spectroscopy was a very problematic thing in terms of sensitivity, because you know that the population sensitivity depends on population, what I have discussed. So we will solve some problems regarding this NMR spectroscopy today also. But going to that before going to that problem, I would like to discuss something related regarding this week's assignment of module 16 to 20, where Professor Sankar Raman has discussed something about a more sophisticated technique which is known as mass spectrometry. So, what is mass spectrometry? Mass spectrometry, as the name suggests, is clearly deals with the mass of the molecule. What is the mass of the molecule? Nothing but the molecular weight. Okay. So it was discovered by J.J. Thomson when he was actually dealing with the isotopes of neon 20 and neon 22, that if neon 22 is somewhat present in the molecule. Hello.
Hello.
Yes.
Sir, your voice is not audible, sir.
I'm not audible.
Yes, sir. Some disturbance is coming, sir.
Uh, is that the case? Hello.
Okay, sir.
Now okay.
Now it is okay, sir.
Okay.
Yes, sir.
Yeah. So mass spectrometry, as was discovered when the people have dealt with the separation of isotopes of neon, and this was discovered by J.J. Thomson. Now, you know, to analyze this is that this is not a spectroscopy, this is a spectrometry. Why this is not a spectroscopy? Why this is not a spectroscopy? This is a spectrometry. Anybody? Why this is not a spectroscopy, mass spectroscopy? This is mass spectrometry. Why? Okay. Yeah. In spectroscopy, you have seen there is some, what is spectroscopy? There is some electromagnetic wave. You have some molecule or some matter which is absorbing or taking this electromagnetic wave, and it is giving some response from which you can determine the structural or any other information regarding the molecule. Okay. And also in any spectroscopy there should be some transition. Okay. So always in spectroscopy there is some transition. But in spectrometry or and also there is transition when there is some involvement of higher excited states. But in spectrometry there is nothing like that. Okay, you need high energy electrons from which you just get these molecular ion peaks or something which we will discuss later, the fragments or etc. So here no involvement of any kind of transition nor any kind of excited states. So here this is not a spectrometry, this is a spectroscopy. Sorry, this is not a spectroscopy, this is a spectrometry. Okay. So to analyze a mass spectrometer, you need some instrument, some setup, which is first is a high vacuum system. Okay, from which you need to pass your sample, and then the presence of high electron source or some ionized chemicals. Different methods are involved in different types of measurement. So depending upon that, different ionization sources are there. So ionization source is the one thing. Another thing is mass analyzer, and from this mass analyzer you will get this m by z ratio, whichever you know. If you have done any mass spectroscopic experiment, you will know that you will get this m by z ratio, and from that you have a detector. Okay. Now there are different steps involved in the recording of mass spectrum. So first you need to vaporize your molecule. You need to vaporization of your molecule into gas phase. Okay. So first thing is, yeah. Okay. So first step involves is the ionization of molecule. So to record any mass spectrum, you need your molecule in the gas phase. So whichever molecule is very easily boiling or very easily volatile, there can you can get easy, convert them easily into the gas phase, and then there is very much they are very easy to be detected using this mass spectroscopy. But whenever there is this problem is there that it is not volatile, then you need to heat the sample so much that you can just make it into the gas phase where it should be detected. But remember that whenever you heating the sample, keep in mind that the sample does not get degraded. Another thing is the ionization of molecules. Okay, so you need, whenever you got your molecule in the gas phase, you ionize these molecules using high energy electrons. Okay, so these high energy electrons actually will knock out some electron or add to some molecule. So this will give you some charge fragments. Okay. Then the separation of ions is done according to your mass by charge ratio. This is actually different for different fragments or different molecules. So the separation is actually done depending upon that. The separation of ion is actually done depending on this m by z or m mass by charge ratio, and The detection of the ion is the final thing. Okay, so the steps involved is you first need to vaporize your sample, or you need to put your sample in the gas phase. Then it will be ionized by presence of high energy electrons, and then the separation of ion, which will be done according to the mass by charge ratio, and there should be some detection of the ions. Okay, these are the different steps involved in the recording of mass spectra. Now, there are different methods for mass spectroscopy. That first is the electron impact ionization, where high energy electron is used, and chemical ionization. These two are mainly discussed in this module. There's electron impact ionization and chemical ionization, and also there are different techniques, and these ESI multi, these techniques will be discussed in the later module. So now you need to know some kind of detector that is used in mass spectrometry. One is the electron multiplier tube, and this another is MCP, that is microchannel plate. Okay, so this electron multiplier tube takes your electron and it multiplies it in a number of times using some setup or some arrangement. So these kind of detectors are used actually in your mass spectrometry. So these are the setup that you should use when you this is inbuilt within your sample. Sorry, using your instrument. Now, talking about this electron impact ionization, first thing is electron beam of 70 electron volt is used. Okay, 70 electron volt is a very high energy electron beam. Okay, so this high energy electron beam is used for electron impact ionization. Now, what is the working principle behind electron ionization? So what will happen? Whatever I have told you, that you got your sample. Your sample will be you got your sample, and your sample will be in gas phase or in a volatile liquid kind of thing. That will be bombarded by high energy electron. So what will happen? Either electron will knock out some electrons from the molecule, or it will add to it, forming some radical, cation, radical anion, this kind of thing. And this charge species will be moved according using some potential. If you follow this Pavia book, you will see a very fantastic diagram where they have easily explained that how these fragments are moving, moving using the accelerated plate, where this movement of these ions is accelerated, or you can retard that, you can control that movement. Okay, so these are the principle that, and this whenever this fragment will go, this will show you some mass by charge ratio. And actually, there is no balance. As Professor Raman has also told you, that don't think that there is some balance inside it that will measure the weight and it will tell you this weight by charge. There is nothing like that. You have seen that there is a correlation between this m by z with the voltage. So it actually measures the voltage, and with measure the voltage and also the distance through which this is traveled, and from there it is converted to this m by z ratio using this relation that was discussed, and you will get this m by z ratio. This is not actually measuring your actual mass, it is just converting your m by z, your result, into m by z ratio. Now, fragmentation of this organic molecule are reproducible under standard ionization condition. This is very much what do you say, advantage, yes, that under standard ionization condition, whatever fragment you are creating, whatever fragment you are getting, is completely reproducible whenever you do this ionization. Okay, this is a very much advantage for this electron ionization. But there is some problems with the AMS, that is, you need to put the molecule in the vapor phase or in the gas phase, which is very difficult for high molecular weight compound like biomolecules, high molecular weight biomolecules. That is very difficult. I'll also get the fragment using using this high energy electron is very difficult with this EIMS method or electron ionization method. So, this is the disadvantage of this EIMS technique, which should not be used for measuring any high molecular weight sample. Now, there comes some new thing which is called chemical ionization. Chemical ionization. The name the suggest that ionization by using chemical. Here you just recall that electron ionization means ionization by use of electron. Here ionization might means of some chemical. What kind of chemical? Here some kind of reagent gas are used, like ammonia, methane, etc. So what is the principle? Principle is you just initially you are just creating ions with these gases or with these reagent gases. You are just charging them, and they will collide with your molecule of interest, and they will actually give you get, the convert this molecule will into molecular ion, which will be detected by your detector. So initially in electron, you are just bombarding your sample with the high energy electron, but here instead of bombarding with the high energy electron, you are just adding some chemical which is ionized beforehand, and it is actually colliding with your molecule, and it will give you the molecular ions. So what kind of reagent gas are used? Ammonia, methane, isobutane, etc. Now in AI, also some this is seen that this aliphatic nitro group, they tend to lose nitro group, but does not happen with CI. Okay. So this completely depends upon the use of this reagent gas and the use of high energy electrons. Yes. Now, one thing comes the nitrogen rule. What does the nitrogen rule say? Nitrogen rule states that compounds having odd number of nitrogen atoms have odd mass and vice versa. You can clearly see you just follow the nitrogen has a mass of 15. Okay. So if you have odd number of nitrogen, so if suppose 1, 3, 5 different odd number of nitrogen, you will see this fraction is always something or 5 always. So it actually varies with the different 1, 3, 5, and you will see whichever odd number of nitrogen is present, you will see a, an odd number. Okay, so this odd number mass will be added up, and you will always get odd number if it is not a odd number beforehand. Okay. Generally, nitrogen is has a mass of 15. This generally creates this odd number, odd mass problem. Okay, and also the compounds having will have even mass. Yeah. Now, the importance of precise mass. Okay, why precise mass is used, and what is precise mass? Precise mass is important because suppose you have some compound, you have two compounds A and B. Suppose both have molecular weight of 60. Suppose, okay. If you do some this urea and acetic acid, I guess if I am not wrong, then these two also. So this kind of thing. So if you just check that these two molecule has molecular weight of 60. So you cannot differentiate between these two. Which fragment is this? Or which one is this one? Okay. So to make this precise mass is important because after decimal places there will be some point, there will be 3 or 4 digits which will be different for A and B here. Okay. So if before the decimal points numbers are same, but after the decimal point the numbers you got is can be same or cannot be same. Okay. So mostly it is observed that they are actually different. So this precise mass is important, and also by means of this there will be increase of the resolution. So what do you mean by resolution? What do you mean by resolution? Resolution. Anybody? Separation of ions are better. Uh, More precise way. How separation of ion is better? That I want to know. Suppose any kind of thing. Suppose in any spectroscopy, if you talk about some resolution, good resolution or good resolved spectra, how will you see it in general? Here not here you are using ion, but in general, how will you see? in general. Anybody else? It gets separated by a distance. Yeah. Okay. So resolution actually defined by you by how much closely you can separate very two close peaks. Okay. So as resolution is a good resolution means instrument if having a good resolution, it actually indicates that it can separate very close to peaks very good. Okay. If resolution is low, that means it cannot separate very closely spaced two peaks. Okay. Just like here, if you have two compounds which have this masses like 60 point something. Suppose for A it is 60.009 and for B it is 60.006. You will see the resolution will be higher to, and in modern mass spectrum instrument the resolution is so higher that it can differentiate between these two. Okay, these two peaks it can differentiate, which is different by 0.003, 0.003. This difference is also can be resolved using today's mass spectroscopy. Now coming to isotopic, that is often seen in mass spectroscopy. Okay, sorry, mass spectrometry. Isotopics are generally seen because you see in mass spectrum there is the m by z, and there is something called here relative abundance. Okay, you will see this will be relative abundance. So some isotopes has relative abundance is quite well, and they actually comes in the mass spectrum, and these are actually seen with the mass spectrum. So isotopes of chlorine and bromine and the variation of the natural abundance in the mass spectrum is can be easily detected. So you know chlorine has two isotopes, 35 and 37, and bromine has two isotopes, bromine 79 and bromine 81. Can you tell me what is the relative abundance of these two? Approximate ratio. What is the approximate ratio of these isotopes?
3:1 for chlorine, 1:1 for bromine.
Yes. Yeah. So chlorine and bromine is the ratio is different. So in the mass spectrum, you will see the relative abundance will be different for this chlorine and bromine isotope. Okay, and this natural radiation is can be easily obtained using this binomial expansion, what is shown in the lecture, that A plus B kind of thing. So from there you can easily determine how much your bromine and chlorine is present using this relative abundance. Now the most probable fragmentation. So in fragmentation, whenever you are discussing about fragmentation, the most probable fragmentation is the one that leaves the positive charge on a fragment that has lowest ionization potential. Okay. So if you are dealing with some fragment, okay, so you cannot just fragment it anyways. There is some rules, certain rules you have to follow, and the following rule is that the positive charge will be on a fragment that has lower ionization potential. This is the sorry, this is the main rule for the fragmentation, and this has a particular name on the name of some scientist. What is the name? What is the rule? This is called Stevenson's rule. Okay, Stevenson's rule actually said that most probable fragmentation is the one that leaves the positive charge on a fragment that has lower ionization potential. Okay. Now there are two different modes of fragmentation. Okay. First mode is you have to cleave one bond to provide an even or odd mass fragment and a radical if no nitrogen is present. Okay. That means you need to cleave one bond. Okay. You need to cleave one bond which will create some species which have even mass or odd mass and a radical. Okay. Or another way, you have to cleave two bonds. Okay, two bonds will be cleaved to produce another odd electron species and a closed cell molecule like water, CO, CO2, it's kind of thing, or ethylene kind of thing. Okay, so two ways of fragmentation is generally observed: either one bond to produce even or odd mass fragment and a radical, and another is two bond fragmentation, which is to create odd electron species and a closed cell molecule. Okay, so generally first one is that is the cleavage of one bond to produce this fragment, it is generally observed. Next, fragmentation generally provides information about the structure of the compound. It's quite natural, you see that from this fragmentation you can generally get the idea about the structure of the compound. Now, branched alkenes fragments more readily than linear alkene. This is quite normal. Okay. So if you have a branched alkene and if you have a linear alkene, you will see the branch one is fragments more easily because its molecular ion peaks are very much long lived, but for linear alkene very short lived because this is very unstable. Okay, the fragments are very unstable for linear alkenes. The branched alkenes generally try to fragment more readily compared to linear alkenes. Another thing is was discussed, that is the McLafferty rearrangement, this abstraction of gamma hydrogen by C double bond X kind of group. So if you have a C double bond O kind of group and if you have gamma hydrogen, so this will be taken up by this one, this is this and this will this. Okay, so this is called McLafferty rearrangement, and this McLafferty rearrangement is very much useful in when you are dealing with some gamma compound of C double bond X where there is presence of gamma hydrogen. Okay. Now there is some fragmentation of butanone. Okay. So fragmentation of this butanone, sorry, this will be butaphenone. My spelling mistake, it will be butaphenone. So butaphenone, you will see two types of alpha fragmentation, one alpha fragmentation, two types of McLafferty rearrangement is happening in this compound. So in first McLafferty rearrangement, you will see that carbonyl double bond O is actually involved with the gamma hydrogen. In the next McLafferty rearrangement, you will see that the gamma hydrogen is extracted by the aromatic ring, and the alpha fragmentation will then give you the peaks which will be most abundant one in the mass spectrum. Okay. Now, retro-Diels-Alder fragmentation. Retro-Diels-Alder fragmentation is just the opposite of this. You have done this Diels-Alder reaction. This is the retro-Diels-Alder reaction. That is, the 6-member ring will be removed and we will get 4 plus 2 kind of thing. You will get back, and then we will see that the where should be the charge reside. The same rule for Stevenson's rule will be applied here, that the fragment charge will reside on the fragment that has lower ionization potential. Now there was a discussion on ortho effect. Ortho effect is nothing but unusual fragmentation of the ortho isomer due to proximity of the functional group. There is some discussion was on orthonitrotoluene and paranitrotoluene, metanitrotoluene. You will see a peak at I guess 119, 120 kind of thing. So this peak was very much higher in intensity for orthoisomer due to this proximity of this functional group, which is not observed for meta or para isomer. Now, the reaction of indole 3-acetaldehyde with ethanol in the presence of ammonium ion intermediate, this was also discussed, that all the fragments that we have got using when the reaction happened, the formation of after the formation of acetal, then they have seen that these fragments can be explained using some ammonium ion intermediate. Okay, this was also discussed, and all the fragments that have come, you can easily see that these are matching with the mass spectra or the fragments corresponding to the mass spectra that you have obtained. Now, the study of H or D exchange reaction by mass spectrometry, you can easily see hydrogen and deuterium, they actually very much differ by their mass. Okay, deuterium has a double mass compared to hydrogen. So if some hydrogen or deuterium exchange reaction is taking place, so how much unit of mass is increased? From there you can clearly see that how much deuterium incorporation is happening in the molecule. Now O18 leveling of ester, this is also can be done, that if you, that whenever you are forming some ester, if it is in the OMe or OR kind of thing, or it is a carbonyl oxygen. This O18 leveling can help to explain you. Wherever you will get this some ester, whenever you will do fragmentation, we will see that the carbonyl part will be separately fragmented, and this, if you just measure the molecular weight of this carbonyl part, you will see that this will differ for O16 and O18. From there you can say that this carbonyl oxygen is the 18 labeled oxygen, or is the OR oxygen is the 18 labeled oxygen. Okay, so these are the things you can do using mass spectrometry. Okay, so there so discussion was mainly on this CIMS or EIMS, that is electron ionization or chemical ionization, where you just use chemicals like some reagent gas like methane, butane, methane, isopropane, etc. And or you can use some high energy electron which will be bombarded, and this will remove or it add to some electron, and this will give you some fragment. Okay, so this was the discussion on mass spectrometry that was discussed in this week. So in today's assignment, I will not do any kind of problem solving regarding this mass spectrometry, because these questions are mainly included in the next week assignment. Wherever there will find in the first three assignment, you will see some, you have seen some NMR data where you are provided with some proton NMR. Today we'll see there will be some carbon NMR. Okay, mainly based on this some carbon NMR, and in the next you will see proton, carbon, and mass. All three will be there. Okay, these kind of questions will be solved. So going to the questions for today. So the first question is, systematically deduce the structure of the organic compound from the given data. Okay, you are given with a data set that contains a lot of data. Okay, so first, whenever you are given such kind of thing, whatever you will do, first you will find this double bond equivalence. Okay, next, before going to this determination of this hydrogen or specification of these hydrogens, I would suggest you just see this IR data. I think you know a bit about IR spectroscopy. Sometimes this IR data is very helpful for you to give some insight that what kind of functional group or what kind of bonds are present here. Okay, so what will be the double bond equivalence here if I want to calculate? Okay, so here the rule is C minus H by 2, what I have explained, but I have not explained if what happens when you have a heteroatom. So if it is monovalent, suppose if X is a monovalent heteroatom, then it will be added by X by 2. If it is a trivalent heteroatom, it will be, suppose it is Y plus will be there.
Is equal to 5.
5, let's see how much it will
Yes,
be.
dB is equal to 5.
Yeah, plus 1. Okay, so these are the rule when you have some heteroatom. So now put number of carbon 9 minus 9 by 2. One heteroatom will be there, half. What is the heteroatom? This chlorine. No tripositive heteroatom, 0. No nitrogen, 0. 1. So 9, 10, 5, 4, 5. Yeah, it's 5. So in your system you have 5 double bond or equivalent kind of system. Okay. So now you need to see what your NMR data suggests. Your NMR data, have anyone solved this question? Okay, we should go one by one. So your NMR data will see that there is a peak at 7.95, which is a doublet of 2 hydrogen and G equals to 7.6. Next one is the 7.6 triplet 1 hydrogen, and next one is the triplet 2 hydrogen. And all of these three are three different values which are mainly related to the aromatic compound. Okay. So in aromatic compound, someone is writing something. It's better you speak just. Monosubstituted benzene. Good. Yeah. So whenever you have some three different kinds of proton, okay, and these three protons comes in the aromatic region 7, 8, 6, 7, 8 region, you can clearly see that three different kinds of aromatic protons are present. Three different aromatic protons are present. Okay. So see, when there will be three different aromatic protons, this could be present very high chance that this is a monosubstituted benzene. Okay. If there is a disubstitution, can there be three different protons? Yes, but whenever you have a monosubstituted benzene, you see all the data, the splitting pattern will be matched. Okay, suppose this is H, this H. You can do this with disubstituted one, you can guess, but you will not see any kind of this difference. You will see that the splitting pattern will not match there. Okay, so here you see this one is this hydrogen and this hydrogen is similar for a monosubstituted compound. This is similar, this is different. Okay, so here this compound, you see this will be doublet because one hydrogen is here. So two hydrogen doublet. You see a two hydrogen doublet. I don't know whether it is this one or this is this one. Okay, so this is two hydrogen doublet. What about this one? This is one hydrogen, two hydrogen. Okay, this will be triplet. So two hydrogen triplet. So I have got a two hydrogen triplet. This one, this is two hydrogens, so triplet. So one hydrogen will be triplet. One is one hydrogen triplet. So the splitting pattern is actually matching whenever I compare it with some monosubstituted compound. So I guess this is nothing but some monosubstituted compound. Okay. Now you see from this IR data what I was talking to you to look at. IR data is 1686 centimeter inverse. If you somebody knows about IR, which will be discussed in the later section, there is some module where we will, when Professor Shankar Raman will discuss IR, they will see that 1690 or 1686 centimeter inverse IR spectrum corresponds to presence of carbonyl function. It could be aldehyde or ketone. Okay. So there is a high chance that presence of carbonyl functional group there. Okay. So you got some presence of this one and some carbonyl thing. Okay. Now you don't know what to do and how much is left. So now you see only two signals are left. Okay, 3.45 and 3.95, and from the splitting pattern, you can see one is two hydrogen triplet, another one is also two hydrogen triplet. Okay, so here what is the molecular formula you get? C6H5. Here another CO is there, so C7H5O. If anybody is not understanding, please tell me. Okay. So it is up to this benzene ring, this molecular formula will be C6H5. Okay. And this carbonyl will be just CO. So add up, you will get C7H5O. Okay. Now, what is the structure of the compound you are given? You are given this one, C9, C9, H9, Cl, O. Okay, this compound is given to you. Now you have solved that this would be the probable thing. So you will just subtract, you will see, you will left with C2H4Cl. This thing is left only. Okay. Now, if you want to match this one with your NMR spectrum, whenever this is possible, 2 hydrogen triplet. Okay. So I have 2 hydrogens, and triplet means in the nearby I have also 2 hydrogen. Similarly, these 2 hydrogens will also give a triplet with 2 hydrogen. Okay. So there must be presence of some CH2 functionality. Okay. But CH2 or any kind of monosubstituted alkene or monosubstituted alkane actually gives you peak nearly 1 or 2. But here you will see the peak values 3.45, 3.95, very, very high value. Okay. That means they are generally connected to some electronegative atom. Okay. So this is the probable structure. C double bond O is connected to this. Okay. If you have seen in this ketomethyl group kind of thing, where these the methyl group is shifted, the methyl which comes nearly 0.9, it is shifted to 2.1, 2.2. Here in case of this compound, wherever you are seeing the peaks at 3.95, that means you are seeing this kind of thing. But how it is getting too much increase? Because it is attaching with another kind of electronegative element which is also taking the electron density from this. This is also prediction. Okay, remember that this is also prediction, which is most probable. Okay, so if this is the case, then we will see this will be 2 hydrogen triplet, this will be 2 hydrogen triplet. So I am done with all my things. Now if I create this structure, it will look like this. Okay, there is the benzene ring, this is the C double bond O, this is the CH2. Okay, this CH2 is there, this is another CH2, and this will be Cl. Okay, so yeah, somebody.
Yeah, I just want to have a clarification. I mean, doubt.
Yes, go on.
When you take a molecule of toluene,
Toluene or stilbene.
yeah, it's methyl substituted benzene ring.
Toluene, yeah.
We get only 2 signals, one for methyl and the remaining aromatic carbon hydrogen as 1 signal. But in this structure, we have the same mono substitution with some groups attached at this position, but we get 3 different type of signals in the aromatic protons.
Correct.
So how we can differentiate? Because in toluene we get only one set of signal for the whole aromatic protons, but here we get 3 different set of protons.
Yes. Whatever you are asking is absolutely correct. Yeah. Actually, the effect is that for toluene, it is just a hydrocarbon, but the effect is this double bond O, this Cl group that is present here, this atmosphere will actually create will be different, which is filled by this one. Okay, so the effect will be different, which will be filled by this one. This will be different, which will filled by this one. This will be different, which will filled by this one. Okay, just like the same thing, whenever you have in a benzene ring, whenever you have some monosubstitution or some kind of group which is attached to a benzene ring, you will see this the directionality. Okay, whether it is ortho-paradirectional or meta-directional. So if some group is ortho-paradirectional, then it will increase or it will decrease the electron density over this ortho or meta position. So you will see the electron density that will be different for this. Okay. So here you will see this kind of compound, it will be mainly orthoparadidictional. Okay. So the electron density, this will be much more dishielded compared to this meta position. So for toluene you didn't see this one, but for this compound where you have carbonyl group and you have CH2 CH2 Cl kind of thing, the electron density will be different for this hydrogen. Have you got my answer?
Exactly. Because methyl group also have some donating effect, no, similar
Yes,
like,
yes, but
but
that will be different from this CO group, right?
I could not able to differentiate exactly how this methyl group in toluene is giving only one aromatic signal, and here it is giving three different signals. Still, I am not clear with that.
Okay. So the minus I effect of this methyl group, that methyl group exact, this is just methyl group is last carbonyl 3 hydrogens. Okay. But
Yeah.
here you will see C double bond O kind of thing. Okay. So the electron attracting ability will be different for methyl and this C double bond O. That is correct.
Okay.
Okay. So the environment, that is some don't know that whether methyl is creating this very much or not. But for this group, for this C double bond O thing, this is creating very much difference in this position. Okay.
Okay.
So if you will see, whenever there is some more group which is much more electron donating or much more electron withdrawing, you will see the difference in the ortho and para products or ortho meta product, right? So this difference actually comes because of the ability of these groups to attract the electron density or give the electron density, right?
Okay.
Yeah. So these hydrogens, so now I am just pointing that which one is which one. Yeah. You see. So the red ones are actually your NMR, proton NMR. Okay. You see this 7.95. This one is the group which is ortho to this C double bond O. Okay. Just follow this C double bond O. Okay. So these groups that are very close to this one, this will be ortho. This will be highly dishielded. Similarly, the para will be very highly dishielded. And I also see the 7.60 is one hydrogen triplet. That is nothing but the para, and this will be, now this meta will be 7.50. Okay, whatever I've told you about that. Yeah. So meta, you will see this will be very less dishielded. So this will be 7.5. Here, these two values, you can see why this one is very much dishielded compared to this one. Why this one is very much dishielded, both in carbon and both in hydrogen, you can see. Yes, go on.
Due to the electronegative atom chlorine, sir, in the presence of chlorine,
Here also
it's
oxygen is
giving
there.
more.
Which one is more electronegative, oxygen or chlorine?
Yes, sir, chlorine.
Which one is more electronegative? Which one?
Oxygen.
Yeah. So you see, this is directly attached to a electronegative group. Yes, wherever you have said is correct. This is directly attached to a chlorine. Okay, and here this is attached to a carbonyl group, which is carbon is actually bearing the oxygen. So it will be much more dishielded compared to this one. Okay, so it will have higher delta value compared to this one. Now, when you are going to point out that when you are getting this suppose you are getting this structure, whatever you have got. Okay, you just want to match it with your carbon spectra. So first thing first, what you need to do, you just need to count how many different types of carbon are there in the compound. Okay, so you see 1, 2, 3, 4, 5, 6, 7. 7 different carbons are there in the compound. Now if you compare to this, you will see if there is some symmetry which passes through this one, okay, so this is one type, this is another, these two are same, these two are same, 3, this is 4, 5, 6, 7 carbons. Okay, so you will see 7 carbons are there. Now if we want to match the peaks, this carbonyl will be highly desilted, just like the proton. This carbonyl here will be highly desilted and it will give you a delta value of 195 that you are getting. Okay, so 195, 180, this kind of range, whenever you are getting this carbonyl, and also whenever you are getting a IR spectra of 1690 or centimeter inverse, you will see that this is nothing but presence of carbonyl group. Also, you will see this 135, 130, this range actually corresponds to aromatic carbon, okay, in the benzene ring. So now which one will be the most desilted one? The one which is attached to the benzene carbon, okay, here. So this one is 135, right? Now these two, you will see that this value is getting more desilted. This is even more desilted, sorry, even more silted, and this one is very much silted compared to this one. That's the thing you have seen in the H1 NMR. You are the same thing you are seeing in the carbon NMR. Okay, so you are done with this compound, which is the structure is this one. Okay. Okay. Now moving to the next question. Systematically deduce the structure of the organic compound from the given data. So this is C4H11N. Okay. Here you can see that from the structure itself, you can clearly see this is C4H11N. Okay. So you see there is no, if not this didn't cross 6. Okay. So there is nothing or nothing aromatic kind of thing will be there, because aromatic minimum 6 or 5 will be there. Here this is 4. So you generally expect there is some aliphatic kind of compound. Now here you are given a delta of 2.6, 2.2 and triplet of 1.1. Now when you find this double bond equivalence here, okay, so you have C4 minus H by 2, 11 by 2 plus N by 2, no heteroatom is there, plus 1. Okay, so 4 minus 11 by 2 plus 1 by 2, this will be 5, right, plus 1. So there will be 0. That means there will be no double bond or equivalent kind of system is present in the molecule. Okay, so this is completely saturated compound. No unsaturation is there. Now from this NMR spectra, whatever you can guess that you have got. Okay, last day I was talking about, I think, ethyl group, right? If anybody remembers or present in the last week assignment, I was talking about ethyl group. Ethyl group, what signal you expect? 2 hydrogen quartet, right, for these two, and you will expect 3 hydrogen singlet. Okay, and if coupling constants are given, you will see the coupling constant will be match. Okay, so the coupling constant, this one is this one, this will match with this one to this one, right? So if you see in any spectrum where there is a presence of 2 hydrogen quartet and 3 hydrogen singlet with the same value of coupling constant, and that's not very much high, you can guess that there is a presence of some ethyl group that I discussed in the last module. So here you can see for this one there is a value of 2.6, which is a 2 hydrogen quartet, and the same thing is there 3 hydrogen triplet. Okay, sorry, so totally wrong. This will be triplet because 2 hydrogens is there. Yeah, sorry. So another is 3 hydrogen triplet, which is present here and also with the same J value or same coupling constant. And you see this value is 1.1, this is 2.6. So you guess there should be some this kind of group. Okay, CH3, CH2 kind of group could be present. Okay, so your CH3 is assigned at 1.1. What is the CH2? CH2 is 2.6. But you can remove, if you remember, I have told you that CH2 cannot go like that. Okay, it comes like 1.4, 1.5 is okay, but it's 2.6 is very much high. That indicate that it is attaching with some heteroatom. Okay, here there is no ring current effect because there is no presence of this benzene ring and there is no presence of the double bond. So there is only possibility that it is attached to some heteroatom. And in you see in the structure, the heteroatom that is only present here is nitrogen. Okay, so there is a high possibility that it is attaching with the nitrogen. Okay, now you just subtract how much have you got now? C2H5N. You just subtract from this C4H11N. So how much would you left? C2H6, if I am not wrong. C2H6. Okay. Now you see a 6 hydrogen singlet. Okay, 6 hydrogen singlet, which indicates that this must be this kind of thing. And here it is attaching to someone where there is no hydrogen, right? If there is some hydrogen, they will show your doublet or triplet or kind of thing. But they are showing 6 hydrogen. These 2 methyls are equivalent. This 2 6 hydrogen. This is triplet. Sorry, singlet. So this 6 hydrogen singlet, and also it you show that this value is 2.2. You see, the value is 2.2. So this much high value, this methyl proton generally come 0.91 kind of thing. This is coming 2.2. There is an indication that it is attaching to another heteroatom, which will getting you this high value of this methyl shift, okay, or methyl delta value. Oh, sorry. So most probably this is the structure. Okay. So N dimethyl ethylene, right? N dimethyl ethylamine, right? So you see here all these peaks are matching, and these peaks will be like where this should be some what is the value 2.2. Okay, so proton spectra actually you have matches. Now you need to verify this structure with the help of carbon 13 NMR. Okay, so you will see if you do some proton NMR spectrum, you will see that this proton spectrum is actually gives some idea about what should be the carbon 13 qualitatively. Okay, that the highest proton will be highest carbon, like that. Okay, so here you will see among these three, this one is the highest one that is obtained for carbon, sorry, hydrogen. Okay, so we expect that this carbon will show highest delta value. So this is the structure, and now if you see the values, yes, this is the highest one, 55. Okay, this is 55, and second, the second most distilled one is this one, which is 48, and most shielded one is this one, which is a very low value, and this is 15. Okay, so this is the structure of the compound, which is verified by mass spectrum. Any question up to this?
Yeah, one doubt to be cleared.
Yes.
The nitrogen is having an attachment to alkyl groups.
3 alkyl groups. Yeah.
Yeah, and one is methylene, but the methylene is going more de-shielding than the methyl group. What could be the probability of this?
This one, right?
You
Yes,
got
you see the difference is not very much. Okay.
No, my question is why the methyl could be of 55, then this methylene of 48. Is it that possibility?
That possibility means.
No, well, I just wanted to know how exactly we are fixing this 55 for methylene and 48 for methyl.
That why I have told you that actually this is the idea we got actually from this proton spectrum. Okay, in proton spectrum you see the methylene. This methylene will have a highly distillate. We will see the proton value of 2.6. So from there we say that if methylene hydrogen is more distillate, that means the hydrogen is attached to a carbon. This will be also more distillate. So from qualitatively, okay, we can say that this one is highest and this one is lowest. Yeah.
Okay.
Okay. Okay. Next, we're going to the next question. Yeah, it's a huge question, but answer is very simple. The following alcohol undergo elimination in the presence of concentrated sulfuric acid, but the product shown here is not its chief product. Instead, its product. Okay. Instead, what happens? Another isomeric 6-carbon alkene form. Okay. The product shows a large peak at 20.4 and a smaller one at 123.4 in its proton decoupled 13C in our spectrum. You need to draw the structure of the compound or the product, and also you need to interpret the spectrum. Also, you need to outline a possible mechanism for the formation of this product that possesses this spectrum. Can anyone help me? What is the possibility? Okay, first you predict the possible mechanism or possible product which actually matches with this structure. Okay, so in your product, whatever you have got, you in the question you have seen the 2 carbon 13 peak. That means two different kinds of carbons are present. One is 20.4 ppm and 123.4 ppm. Okay, so two different kinds of carbon are present in the compound, and also your compound is a 6-carbon alkene, right? And this alkene is produced from here, this alcohol. Okay, so if I go one by one, yeah, 13C is showing 2 peaks at 20.4 and 123.4. This is a 6-carbon alkene. Now you will see now you will see I would like to draw the structure. So in presence of H2 of SO4, what will happen? First thing, what will happen? H2SO4 is nothing but some acid. Okay, you know. So you will just give your proton. Now what will happen with this proton? If you have some alcohol, there is a high chance that it will get protonated like this. Okay, I'm going to the mechanism. It will go like this. Okay. Now what will happen? The high chance that it will get eliminated minus water, right? Like this. Now the thing is, whenever you have something like this, okay, something like this, so what will happen from here? Your first product, whatever you have seen, just eliminating this hydrogen. Okay, so what will happen there? This hydrogen will go and this plus charge will be neutralized, will give you this product wherever you are creating this. Okay, instead there is some chance of local rearrangement. Okay, so rearrangement will happen. Why it will happen? You see, this is 1 degree carbocation. Okay, so if this methyl migration happens, it will create this one carbocation. So this is nothing but 2 degree carbocation. Okay, this will create 2 degree carbocation. If methyl group migrates from here to here, you will get 2 degree carbocation because carbocation will be now there. Okay, if any of these methyl groups moves, then this will create another carbocation over here. This will be again 2 degree carbocation. So is this the only way that you will get maximum 2 degree carbocation? Because you need to stabilize your carbocation. So what will happen? Instead, molecule will, what will happen, that this hydride, this will get transferred. Okay, why this will transferred? Is there any benefit that it will get transferred and I will get something very interesting? Yes. What is the benefit? Benefit is that you will get a carbocation which is nothing but a 3 degree carbocation. Okay, so what will happen generally, if anybody who lost some water molecule, this is the most probable that this will lose some water and then hydrogen will go and forming the double bond and you will get the product that is mentioned in the question, this product. But there is some also possibility that a hydride migration occur. Okay, why hydride migration will occur? Because hydride migration will give you this kind of carbocation which is very much stable due to this one. Okay, this carbocation is very much stable. Now can anyone tell me why tertiary carbocation is highly stable? Very basic organic chemistry.
Inductive.
Inductive effect of methyl
Plus inductive.
plus inductive. Anyone else? Inductive effect.
Hyperconjugation.
Exactly. This is the main reason, hyperconjugation. Yeah. How many hydrogen is there for hyperconjugation? 3, 3, 6, 1 is 7. 7 hydrogen is there. Okay. The main reason for this stability of tertiary carbocation is the hyperconjugation. So hyperconjugation stability will give this tertiary carbocation much more stable. Now what will happen? Now the thing will be, this hydrogen will be lost. I'm just changing this hydrogen. Ah, no, it cannot remove. Now I am writing the structure like this. Carbon, hydrogen, methyl, methyl. Okay, and here is a plus sign. Now why is it possible that now this is a common process that this will do to hydrogen. So you will get tetra substituted alkene, right? We have done some work on this in the NMR, that these 4 methyl groups are there. This is some expected product. Now we are made to match it with some, with our data of carbon 13 NMR. Is this the product or not? You see, these 4 methyl groups are equivalent. You cannot distinguish between them. And these 2 carbons, they are also equivalent. So you will see, for this 4 methyl, you will get 1 carbon signal. For this 2 carbon, you will get only 1 carbon signal. Okay, so 2 carbon signals. 2 different carbon signals. Whatever I have told you, that whenever you give some carbon signal, count how many different carbons are there in the molecule. I see that 2 carbons are there, and I mean also this is suggesting that whatever data I have given, it actually matches, because this methyl proton, methyl carbons actually comes near below of 20, nearly 20, and this double bond carbon, alkyne carbon, alkene carbon, this actually comes near almost about 120. Okay. So this actually signifies that this is the product. Then this is the answer, that a primary carbocation which rearranges to a tertiary cation, a hydride shift, and then U1 elimination to form this tetrasubstituted alkene, which is named as 2,3-dimethyl butene. So this is the product, and this is the compound that we are talking about. Okay. Okay. Now going to the fourth question. You have to systematically deduce the structure of the organic compound from the given data. So molecular formula is C5H7NO2. Okay, this is the molecular formula, C5H7NO2. Now you have to find that what kind of molecular structure is this, and your NMR data of proton and carbon is given. And since I told you to count the number of carbon, you see 5 carbons are there. 1, 2, 3, 4, 5. 5 carbons are there. So in your compound of C5H7NO2, one thing you are sure for sure, that your 5 carbons, C5 is there, 5 carbons in there in the compound, and all of your 5 carbons are different. Okay. So now you find double bond equivalence. Which is nothing but C minus H by 2 plus N by 2 plus 1. 7 by 2 plus 1 by 2, this is 2 plus 1, 3, I guess. 5 minus, 7 minus 1, 6, 6 by 2 minus 3, 5 minus 2, 2. Yeah. So 3, there is 3 double bond or equivalent kind of system. Now, also in the NMR, you see there is no value above 6 or 7. Okay, so that means there is no question of any kind of aromatic compound. Okay, this is also an aliphatic compound. How is the aliphatic compound? Okay, now whenever I told you that 2 hydrogen quartet with 3 hydrogen triplet is present with the same value of this coupling constant, there is a high possibility that the presence of some ethyl group. Okay, 2 hydrogen quartet along with 3 hydrogen triplet, most possible existence of CH2 CH3 group. Okay, is the most possible existence of CH2 CH3 group. CH2 3. Okay, now only you see here in your carbon there is 5 data, in your proton there is 3 data. Okay, that means there is some carbons which is not attached to some proton. Okay, there is high possibility. I am not saying that this is correct, it will always happen, but there is high possibility that there is some carbon which is not attached to some proton. Let's see. Okay, so this ethyl and CH3 and methyl and ethyl, this group is there. Now what we are left with? 2 hydrogen singlet of 3.5 delta value. Okay, so what is this could be? Okay, now you can you go to their carbon 13 spectrum. Okay, so your 165 carbon 13 value is generally indicative of the presence of C double bond O. Okay, C double bond O. So you have got 3 carbons. How much is gone? Collect C123 H5 O. I think C3H5O. Yeah. Now I have the formula C5H7NO2. So there is another nitrogen also. Good. So you see the C3H5O. Okay. So if you just subtract it, we will get C2H2NO. This fragment is also left. Okay. Now if I go to whatever I talked about carbonyl, yes, here I have shown you the carbonyl value is 195, but here I am telling that carbonyl is 180. That means, oh, sorry, 165, yeah. So here there is a chance that it is attached to some electronegative atom, either nitrogen or oxygen. So if this is the case, then you will see that this oxygen or nitrogen will pull the electron density over the carbon. So this carbon's electron density will be much more increased. This will be more shielded. The delta value will be low. Okay. Now, if nitrogen or oxygen is gone, we will left with C2H2 kind of thing. Okay. So if nitrogen is gone, minus nitrogen is gone, then we will left C2H2O kind of thing. If oxygen is gone, where it is gone? It is gone to it is attached to carbonyl. Okay. If oxygen is gone, you will see it will be C2H2N. Okay. Now, how I will go know that which one way I will proceed and which one is correct? This will be given information by your this one. This NMR data. This is 2 hydrogen singlet. That means this 2 hydrogen is actually not exchangeable with any kind of thing. That means it is not an H2 kind of thing or OH kind of thing. That means this hydrogen is actually attached to any carbon. So CH2 will be lost. Okay, so you have some CH2, and you will know the CH2 doesn't come here. 3.5 is very high value. That means it is attached to some or any kind of heteroatom. Okay. Now, if CH2 is removed, if from there CH2 is removed, now from here CH2 is removed, what we were left with? Okay, here from CH2 is removed, we will left with CO. Here if it is removed, it is CO. Oh, this will be CN. Now you have got two values of CO and CN. So finally, if you have got that in your compound there is some ester group. Okay. In your compound there is some ester group. In your compound there is some CH2 kind of thing. Yeah, CH2 kind of thing. Okay, I will take the red one. Yeah. So in your compound there is some ethyl group. There is some CH2 kind of thing. There is some C double bond O kind of thing, or C double bond O N kind of thing. Okay, these three possibility we know. Now we are left with this CO is possible or CN is possible. Okay. So if CO is possible, you know this carbon oxygen will tend to try look as this one. Okay. And if CN is possible, you look it will be this one, right? And if CO is present, so with along with this CO, C double bond O, I will get another CO which will be around 190 or 190 kind of thing. Okay, but if CN is present, I will get another peak of carbon 13 which will be nearly 110 or 120 in this range. Okay, so if CO is present, only that from this if CO is present, you will get another peak at 195 or 100, 190 to 200 in the range. But if CN is present, you will feel another peak at 100 to 120. Okay. Now you see your mass spectra. Where you where you see your carbon 13 NMR. You are seeing a peak at 115 nanometer peak of ppm. Okay, which indicates that presence of CN is there. Right. So from here you see that there is no peaks at 190. That means CO is not present. But 115 there is a peak which is present, means that cyanide is present. Now going back to this one. Okay, if cyanide is present, what will happen? Cyanide is present, there is some CH2 is there, and if CH2 is there, CH2 from this way cyanide is gone, so this carbonyl is attached to some oxygen, so this is the group. Okay, now I have deduced that this is the group. So what I have C double bond O. Okay, now you see this ethyl, what is this value? This value you got 4.3. Yeah, 4.3 got it. Okay, so 4.3 value is a high value, which indicates that it is attached to very much higher electronegative element, which is possible that it is attached to this one. Okay, this is attached to this one. So this is one thing. So I am left with some CH2 and CN. So which is one possibility that CH2 is there, and from here CN is there. Okay, and this high value of CH2, here you see CH2 value, this value is 4.3, here 3.5. Okay, very much less desilted because it is attached to some carbon which has triple bond. It is attached to a carbon which has a double bond, and also nitrogen is here. Okay, so this will be more desilted, so this will come 3.5. So this is the most probable structure, and you see 5 different carbon, 1, 2, 3, 4, 5. Okay, so this is the structure that I am talking about. The CH3, CH2, O, C double bond O, CH2, CN. Okay, and these are the peak positions that which one is coming where. Okay, you have got this position, you got this problem, how it is solved.
Yes, sir.
Okay. Okay, moving to the next question. This is a pretty simple follow-up question.
Can I have a
Yes, sure.
In the first problem, we have seen the carbonyl group was been appearing in the carbon NMR as 195.
Yes.
Now it is coming as 165 in spite of an oxygen adjacent to this carbonyl.
Yes.
What could be the probability there? We are having a highly de-shielded value of 195 for the carbon of carbonyl.
Yes.
Here it is only 165.
Yes, that I have explained just that it is attached to some oxygen. Okay. Now what will oxygen do? There is a high chance of this resonance, right? Right?
Yeah.
So oxygen, there is a chance that it is involved, this lone pair or electron will involve with this one. Okay. So in around carbon, electron density will be increased or decreased if oxygen lone pair is involved.
Come again?
If oxygen lone pair is involved with it in resonance, so the electron density around this carbon, will it increase or decrease?
Usually, when you have an electronegative atom adjacent to it, it will be always having a decrease in value.
Okay, but yes, you are correct. But if his lone pair is involved with it, so it will actually push his electron towards this one. Okay.
Okay.
So like this, so it will actually, whatever you see their electron density over here, when there is some ester functionality, so if electron is involved here, so it will increase the electron density. So if electron density is increased, so it will be more shielded, right?
Yeah.
So if it is more shielded, then its delta value will be decreased. That's you are seeing here. Got my point?
Yeah, almost the same thing has to be explained for if you have a carboxylic acid group or an ester group. If it is
Yes,
it will, yeah, okay. Thank you.
Okay, now coming to this problem where I have this C6H12O2. Okay, molecular formula. Now you see 4 different carbons are there. 4 different carbons is present in this molecule. Now you see that what should be the double bond equivalence?
1.
1. Let's see.
Yes.
6 minus. Yes, it's 1. So there is one double bond or equivalent kind of system that is present in the molecule. Now you see only 2 proton signals. Okay, only 2 proton signal. What is written that with a 1:3 integration ratio. Okay, so if this coming from 1 hydrogen, this will come for 3 hydrogen, like this. Okay, so in this compound you see this 1:3, and now you see this carbon spectra. There is some 180 nanometer, 180 ppm carbon 13 data, which is very high chance that carbonyl attached to some heteroatom, what I was talked about, is present here. Okay, some heteroatom X kind of thing, this is present here. Now if carbonyl, what heteroatom is present here? Oxygen only is there. So it is very possible that it is attached to some oxygen here. Okay, now I am removing just CO2. I am removing just CO2. What I am left with? C5H12. Right? So I am left with C5H12. Okay. Now what can I do? So from this structure, 1:3 integration ratio, this is actually predicted that this kind of group is very much present, because this tertiary butyl group is very much possible that it is present in the molecule. Okay, and since it is attached to a carbon and this is attached to something, so there will be no hydrogen. No hydrogen will be there. Okay, so from there you will see that this will be methyl group, just 1.2 or 0.91, that error range. Okay, so that in that range it will come, and this 3, since this is following 1:3 integration ratio, so there is a chance that there should be some methyl. Okay, for this 1, and for this 3 methyl group is 3. Okay, so if you count proton, there is 3 proton and there is 9 proton. So you see this integration ratio is followed 1:3. This is the prediction. This is the prediction that this is most possible presence, that 1:3 integration ratio. Now the problem is, you see both of them are singlet. That means they are connected to some carbon which possess no hydrogen, or some heteroatom which possess no hydrogen. So from this methyl, if this is the methyl one, then I should see that this 3.7 singlet, that cannot be present, that cannot be possible if it is attached to some carbon. It is only possible if it is attached to some heteroatom like oxygen. Okay, so I have shown that only oxygen there is carbonyl attached, so there is a chance that this is attached to this one. Okay, now what is this total count? C1, 2, 3, 4. So this is C4. These hydrogens will be H9. Okay, if you count C4, H9. Now if you add CH3, C5, H12. Yes, it is matching with this. So I first need to write this one, then I should match the carbon signal. So how many different kinds of carbon will be there for these three? So I'm writing what is the structure. This CH3. This C. Okay. So this is attached to some carbonyl. It is attached to some oxygen, and this is CH3. Yeah. Now you match the carbon signal. So 180 was this one. Okay. So 180 is this one. This one. Next is 52. Which one should be 52? You see whatever I have told you. Go to the structure. Okay. So this one, this methyl, is highly distillate. So it is attaching to some oxygen. Okay. This is attached. This is also distillate, but this is attached to a carbonyl. But this is directly attached to oxygen. So this is highly distillate. So this will be 39, and this one will be 28. So this one is the structure. This is an ester. Okay. So this is a compound, and this is matching with your NMR and 13th NMR and 1H proton data. Okay. Okay. Next, I'm moving to the next question. Yeah. So you need to systematically deduce the structure of the organic compound from the given data. This C10, C10, H9, NO2. Okay. So if you find DBE or double bond equivalence, you will find it will be 10 minus 9 by 2 plus 1 by 2 plus 1. We will see 9 minus 6. Sorry, this will be 8. 8 by 2 will be 4. So 7, I think. 11 minus, yeah, 7. So there are seven double bond or equivalent kind of system that is present in this molecule. So this is a little bit tough problem because you have so much data. So whenever you have some IR data, you just follow this. Okay. Whenever you will follow this IR spectroscopy, you will see this actually corresponds to C triple bond C or C triple bond N kind of functionality presents. Okay, this value. And this 16,050 to 17,050, you can close your eyes and say this is nothing but a carbonyl. Okay, carbonyl group. Yes, Sarita, or do you want to say something?
The screen is not visible.
It is not visible. You can see now. Can you see it? Can you see it?
Yes, sir, visible.
Visible, no? Yeah.
Yes, visible.
No, sir.
Someone is
Sir,
saying
visible,
visible,
sir.
someone is saying
No, sir. Might be she
visible.
has to rejoin, sir.
Hi, yeah, you can do it. You can
Yeah,
rejoin, but
that's a problem,
there
sir.
may be some issue with your internet connectivity. Yeah,
Okay.
yeah. Okay, so now, so this from this information, I can say that what kind of functional group could be present from this IR, that it could there could be C triple bond C or C triple bond N or any kind of carbonyl functional group. And also generally carbonyl functional groups comes nearly 16,080, 60,090. Okay, this range. But it is 1724 centimeter inverse. This is a very high chance that ester group is generally high, very high chance that ester group is present. Yeah. Now, from here, from this NMR data, you go down to the NMR data, you see there is peaks of 8.2, 7.8, which indicates that in your aromatic region. Okay, in aromatic region, you just see the spectral pattern. You will see A prime, B prime pattern with 4 hydrogen. Okay, which it clearly indicates on the first day I have told you that this indicates that A prime, B prime pattern with 2 values on 4 hydrogen. This indicates actually para disubstituted compound. Okay, so this actually indicates a para disubstituted compound. Now I have to match all other proton signals. Okay, so 4.5 quartet 2 hydrogen, 3 hydrogen triplet. Okay, same thing, the same thing I am talking, that this is a 2 hydrogen quartet of 7.5 hertz, and there is a 3 hydrogen triplet of 1.4, sorry, 3 hydrogen triplet of 7.5 hertz. So the coupling constant is same, and this is following a pattern which clearly indicates there is a presence of ethyl group. Okay, you just prediction is not okay. Okay, finally you have to just give the values and then you have to match with that. Okay, just first for the first simple case I am just doing the prediction. Okay, so CH2 CH3 group is present, and also I have seen the presence of carbonyl and cyanide. So all this you sum up. Okay, so what it will give, you get C6H4. Okay, 4 hydrogens are there. Four hydrogens are there. So you from C6H4 you have got Cn, so plus Cn. You have got, oh sorry, this is not a bonded. I have not bonded. This is CH2 CH3, so add it, I get C2H5 and add CO. So count 6, 7, add 9, 10. C10 H4 5, 9 NO. So what I am left with? C10 H9 NO2. So I am left with one oxygen. Okay. So this whatever I have told you, that there is a presence of this oxygen. Right? Now where cyanide group is present? Cyanide group is present here. Okay. Here cyanide group is present. But now what about this ethyl group? Just they directly present with this carbon, which is this possible, because if you see this CH2, this hydrogen, the splitting pattern, you see the splitting pattern actually for the CH2, I say this hydrogen is coming at 4.5. So this is high chance that this is attached to some heteroatom, oxygen. Okay. So oxygen is attached to this one. This is attached to also carbonyl. Okay. So very high possibility that it is like this. Okay. This is like this. So I predicted the structure. Now I have to match it with the carbon 13 data. Right. So I get 165. This is this one. 165. Yes. 135. This is this cyanide. 132. 132, 130, 116, 62, and 18. Okay, 7 carbon signals are there. You see, count the carbon 1, 2, 3, 4, 5. Okay, I'm marking 1, 2, 3, 4. These two are equal 5. These two are equal 6, 7, 8. But I have given 1, 2, 3, 4, 5, 6, 7. Is this wrong? 7 signals are there? No, this is not wrong, because this carbon signal is actually coming within these two, 135 and 132. This comes nearly 134 kind of thing. Okay, so this one actually comes nearly 134. So if I draw, sorry, not this one, this one nearly comes, this was missing in the question, this one nearly comes nearly 134. Okay, so you just match with the other of the other carbon spectrum. It is 165, 62, 18, and all the peaks are there. Okay, just rubbing it up, if you can clearly see it. Just excuse me for just 1 or 2 minutes. Okay, I'm just coming. Just coming. Yeah, sorry guys for the delay. Okay, so this is the compound that I was talking about. Now you have any question? Do you have any question?
Sir, in this compound, total 8 different carbons are present here, sir.
8 different carbon. Yeah.
Yes, sir. Is C triple bond and 1 carbon, sir.
Yes,
Next,
yes. I've told you
two,
already.
three,
8 carbons are present. Yeah, you're
yes.
correct. 8 carbons are present here. But this
But
carbon, this value is very close to this value. Okay, this 135. Okay,
Okay, sir. Okay, sir.
this 135, this cyanide, this one and this one is very close. Okay, so in the question they are given that's only one value is there, so because these values are very close.
That was 7 only appearing in the carbon only.
Hmm?
For the prison only 7
Yeah,
7
yeah.
T13 one.
Yes, 7 and
Okay.
8. Yes. Any more question?
So as you mentioned, there is one missing carbon values in C13 NMR. Is it right?
Yes.
So we have to include 134 for one of the tab.
Actually, this is not missing. This is actually hidden. Okay. So this 135. So this carbon value is almost 134. Okay. So the 134 point something, and this is more likely to 135 close. Okay. So this will you see only like a simple single pattern, or but if you closely zoom it, you will see there should be some difference. Yeah. Got it?
Yeah. In case if the structure, if the carbonyl group is going attached with this nitrile group, will the structure will be okay?
Carbonyl group.
Instead of having an attachment in the fourth position of carbonyl, if it is carbonyl attached with the nitrile function, maybe any chance for the structure?
Like this.
Yeah, this should be reversed. This carbonate should come here and then nitrile should go to the other side.
COCN.
And the remaining is OCS2, CS3.
C double bond O, C triple bond N. This one you are talking about?
Yeah, and the remaining is the same. They all alkoxy.
Like this. Yes. Good prediction.
So
The spectral features will not match. Okay, first of all, your this one will not match. Whatever. This yes.
which one you are talking, sir?
This higher. I told you.
1724.
Yeah. If your normal carbonyl is there, okay, so there will be only 1680, 1690 kind of thing, but this will not match. And also, this photons, this value you have seen before that this value comes like 4 point something, 4.5. Okay, if it is very close to this aromatic ring, this value will be even higher. Okay.
Even now, if it is attached now with an aromatic ring, we have a the wave number is decreasing because of the conjugation with the carbonyl. Actually, the normal value of ketone will be getting somewhere around 70.
In IR?
Yeah, IR.
In IR, in normal ketone is 1690, 1680 kind of thing.
No, 1700 plus, no? That value now.
Not 1700 plus. That means this is actually the, what do you say, this error range. Okay. So 1650 to 1750, whatever you get idea that this is a carbonyl is present. Now it is present in lone or bare carbonyl, or it is attached to some heteroatom. That actually depends upon this this frequency. If it is attached to some heteroatom, then its frequency will increase. Okay.
Okay.
Any more question? Okay. So if you know there is no more question, so this is the questions that I have discussed for this NMR. So I would like to give you a question that you should try in your at your home, and I will give you answer in the next session. A very interesting question. You have to systematically deduce the structure of this organic compound from the given data. C4H6O2. Okay, don't get afraid. It is not a aromatic compound. Okay, this much hint I have given you, and also you can see from this molecular formula the structural properties are given, and this DQ actually stands for doublets of quartet. Okay, DQ stands for doublet of quartets. Okay, you just try to solve this and match this with the carbon spectrum. Okay.
Okay, sir.
Okay, you try it, and we'll start the next session by solving this question, and we'll solve much more question with inclusion of this mass spectrum. Okay.
I have the last question, though, sir.
Yes, go on.
Actually, in one of the assignments, they have given with the A prime with the BB prime type of signal in NMR with J value of 8 hertz.
Yes.
But they have not given how many number of protons in that.
Okay.
So shall we consider it contains 4 hydrogens?
Yes, you consider it and you just check all the values. Okay. So if all the values are like this, I mean all the proton signals, if you just can match all the proton signals, then you are correct. Sometimes people have mentioned or sometimes people don't mention. Okay.
Okay.
So
Okay.
from A prime, B prime pattern, you just predict that this is a paradise associated compound.
Yeah, that's
Yeah,
right.
that's the thing, and then just match it.
Thank you.
Okay. So I think you all have taken screenshots if you need it. Okay. Yes, Sarita. Yes.
Can I get the solution of assignment number 1 and 2? I have
Yes.
not attended the session.
If you just log in with your ID and password, then you will see in this WAM portal. You will see that this is already given. This first one and second one. And if you need this live session, I have uploaded in this YouTube. You can see it there. Okay.
Okay, sir. Thank you.
From YouTube, you can see there. So this public seed link there is there. From there you can visit it. And
What
also
is
the
the
site.
website? Website. YouTube.
I think YouTube link.
Huh?
Just a second. Public state, I think. Just a second.
Yes.
Let me